unstable Big Bang formation.
Thanks, Maxine, and thanks to the organizer for the invitation. It's great to be back in Toronto after quite a few years since I graduated from here. And thank you all for staying. I know it's the last talk and everybody's tired. I'll try to make it as entertaining as possible and avoid the technicalities. Okay, so I will be talking about joint work with Jared Speck. And since everybody, like Hans and Warren, already gave quite a good introduction on Big Bang singularities, I'll try to go through this briefly. Okay, so the model is again the same that Hans talked about. Einstein coupled to a scalar field or vacuum if that scalar field is 0. We have these spatial dimensions, initial data that satisfy the constraints, okay, Hamiltonian constraint, a momentum constraint. We have a well-posed initial value problem, unique maximum development, etc. And the main topic of interest is the study of the dynamics of the Kastner solutions. So Warren already wrote down the Kastner metric. So this is in toroidal topology. The scalar field, again, as Hans mentioned, the leading order behavior. So this is the multiple of the logarithm. And okay, the constant doesn't really matter. These parameters, the pi's and b, which are constants, have to satisfy these algebraic restrictions. Pi is less than 1. So otherwise, you get the 1, 0, 0 degenerate case, which doesn't have singularity. And okay, this is defined in the half line, and as t goes to 0, as we heard before, there's a curvature singularity, so things diverge. And the main question is, what can we say about the dynamics of this singularity? Okay. All right. So you can think of prescribing. So this is relative to the initial value problem, right? So you can think of prescribing initial data on t equals 1, let's say, which are close to the Kastner initial data, the homogeneous initial data. And the question we want to answer is whether there's a Big Bang singularity in the past. We know that it's past incomplete, thanks to Hawking. And we would like, if there is a Big Bang singularity, to understand what is the asymptotic behavior, if there exists one. Is it like Kastner or is it different? And we already know, we heard in the previous talks, what is the story. So the main type of behavior that we want to obtain in the problem that I will discuss is what I call here Kastner-like. Before it was called AVTD, or other words for the same thing. So you should think of having a singularity that's synchronized, let's say at the level set of t equals 0, and the metric to lead in order looks like this. It's sort of like Kastner, but it varies in x, so it's inhomogeneous. So the pi's now are functions. The coefficient, the leading order behavior of the scalar field is the same in terms of t, but the coefficient can depend on x. And the one forms that diagonalize the metric, these are all also x dependent. Okay, and in Hans's talk, we heard that these pi's andcij's are related to the geometric initial data, the singularity of these solutions. Okay. And since we're studying the stability problem, the dynamics of the homogeneous solutions, you should think of an affirmative answer in the sense of closeness for the asymptotic data, right? So we will say that Kastner solution is stable if you have this behavior and the corresponding asymptotic data is close to the background values, which are constants. Okay. Okay, so in particular, Cij is close to delta ij, the pi is close to pi, etc. Okay, and the conjecture for the dynamics of these solutions is due to BKL. And okay, the original argument, and then of course it was generalized in many ways by other people and BKL as well in various papers. So the bottom line is that if you have this apocriticality condition in your model, like the family of solutions, like okay, the either Einstein vacuum or scalar field allows for this possibility, then after potentially finally many bounces in the sense that Warren described, you will have stable dynamics, like Kastner-like behavior. If your original background that you're perturbing, Kastner solution already satisfies this, then there's not going to be any bounce. You're going to immediately be stable. If not, then the bounces are infinitely many and there's no asymptotics. All right, so at least that's vaguely the expectation. Of course, there's much more complicated than that, but I'm going to be talking about the first point when this restriction is already valid for the background. So then there are no bounces, and the picture is much more is simplified. Okay, and of course examples. So this subcriticality condition that we already saw in Hans's talk is allowed in the presence of a scalar field in 3 or higher spatial dimensions. So in 3 spatial dimensions, actually, it is equivalent to the Kastner exponents being positive. Okay, so for the scalar field, this is possible, and in vacuum, it's not. This is actually very easy to see. So let's, if you go here, if they're all positive and less than 1, then the square is going to be strictly less than 1. That's the sum. So you need B to be non-zero in order for this to be possible in 3 spatial dimensions. If you really want vacuum, then you have to enlarge the spatial dimensions, and there's a magic number that you can compute. So for 10, greater or equal to 10, it's possible to satisfy this restriction. Okay. All right, and we will be talking about stability, and we already saw Hans mentioned the results, or maybe a subset of them. I'm also not 100% up to date on the recent developments. Like in the last couple of years, there's been quite a few. But it all started in the seminal work of Rodniansky and Speck. I think the paper on the archives from 2014 for the near isotropic case in 3 spatial dimensions, which kind of opened this direction. So there's the sort of proving stability was kind of made possible. And they did it for the stiff fluid, but okay, it's very similar to the scalar field. In the case where all the Kastner exponents are near equal, okay? Then they sort of enlarged, so they relaxed this condition by including a moderate, what they call moderate range of Kastner parameters. And in order to satisfy, so this is in vacuum, and in order to satisfy this inequality, you have to have quite high spatial dimensions. Basically, morally, like, you know, if you increase, more you increase the spatial dimensions, the smaller Kastner exponents you can have, okay? And in particular, if they're all small, then the algebraic combination that we saw before is going to be less than 1. So it's possible. Okay, later on, we got the full range. And by now, we can say that also, thanks to Hans and Andres and other people and Todd. So I made sure to list everyone in the room. So no. So I hope I didn't forget people. So we can localize it. We have very recently, I was really excited to hear that we can have asymptotics for the full spatial geometry, which was missing from all of the previous works before Andres and Hans's paper. You can add matter, like fluid, Maxwell, Vlasov. You definitely need, so all the time you need scalar field or steep fluid so to have this restriction, but you can add more stuff. And yeah, the method works. So there is a robust, quite robust method to prove now stable Big Bang formation and get kind of like all the information you would like to have. And okay, now either you have to go to oscillations or try to make minor improvements of what's, so okay, you know quite a lot of stuff, but there's still things you can ask. So this one what we will say in this talk. But essentially, like the important thing, the singularity formation and the asymptotic behavior, like we already have. Okay. Now, in this presentation, I would like to emphasize on the two different methods that are usually employed to get this stable Big Bang formation, which distinguish between the near isotropic case and the full range or moderate range, or if you have anisotropic background Kastner values. Okay, and this has to do with the kind of energy estimate that you can obtain at top order. So the proof is divided in mainly two steps. One is the ODE argument that Warren described very well in his case of Gaudi class. And then the other is, again, the top order, which, again, Warren told us about the main feature. So basically, when you define an energy that controls your solution and try to estimate it, because of the singular background, you're going to get a coefficient which is borderline non-integrable, this 1/t. And this C star depends on the background Kastner exponents. So there's various mixed terms that you have to kind of estimate. And okay, at the end of the day, this tells you that the energy cannot blow up faster than the inverse power of T. And the whole point is, what is the C star? Okay, so in the near isotropic case, so Rodniansky and Speck first noticed that there are cancellations in the estimates that allow you to have like a small C star. Epsilon here is how close you are to the background initially. Okay, and they call that approximate monotonicity, but essentially means that C star is small. Okay. Of course, this relies on certain cancellations taking place, and for some problems that might not be the case. So then, for the full range, or let's say more anisotropic Kastner exponents, a new method was introduced as far as the energy estimates are concerned, which allows for very degenerate top order estimates. Like you can have C star as big as you like, as long as it doesn't depend. So it only depends on the Kastner exponents and not, let's say, how many derivatives you're taking. Okay. Okay, and then the optimal estimate, at least for the second fundamental form, or the key parameters, the key variables that you need to control, are recovered at the very lower orders. So this was, I think, inspired by Christodoulou's work on shocks that was also had this kind of degenerate top order estimates. Anyway, so these are the two approaches as far as the energy estimates are concerned. And the main question that of interest here is that whether this is an actual phenomenon of the dynamics, or is it just that you cannot do the estimates like in a better way? Okay. And what is why do we care about it? It's a little bit secondary, but okay, I would like to describe it here. Let's say we don't care about approximate monotonicity and we can live with degenerate estimates. What does this imply? Well, one is that you have to take too many derivatives in order to close the argument. So in also what Warren talked about, let's say you have a quantity, you want to show that this is less singular than some power of, let's say, 1 over t. And this has to do, let's say, with the spatial variables that have to be, the spatial derivatives have to be, let's say, subleading relative to the time derivatives. Okay, and at the lower orders, let's say L infinity, you can do that. But at high orders, like at top order, you have this energy estimate, which is very bad. Okay, but by taking, and then when you want to control the rest of the variables, at some point you're going to see derivative of that or two derivatives, etc. So you would also like this to be less singular than 1 over t. And what you do is you interpolate between top order and L infinity. And if you have n sufficiently large, you can ensure that this contribution from the top order estimate is very small because C star is independent of n, okay, the number of derivatives. So then, okay, there also, you need Q, you don't, I mean, okay, Q is less than 1, but it's kind of like lower bounded by the number, the values of the Kastner exponents, the background Kastner exponents. So if you're very close to the degenerate case, 1, 0, 0, then Q is very close to 1. So, okay, in order to make sure that this is less singular than t to the minus 1, then delta has to be very small, like, okay, and hence n has to be very large, not only relative to C star, but also relative to the background Kastner exponents. So in other words, if C star is large, n has to be large. If pi is going to 1, n has to be much larger, etc. And going to infinity in these two endpoints, okay? All right. And now this affects, let's say, the regularity of the asymptotic data. So in what Hans talked about, in order to get this convergence and the geometric data at the singularity, you need optimal bounds on this expansion normalized Weingarten map, which is a renormalized second fundamental form. And if you lose, so if you don't have a good bound on that, then you don't have convergence. So asymptotic data convergence in this scheme with highly degenerate top order estimates only, you only obtain it at the very lower orders that you can improve, right? By sacrificing derivatives. And okay, then you should ask like whether this is an actual phenomenon, as we said before. So do asymptotic data lose regularity? So this could be fundamental if indeed the asymptotic data, the Kastner exponents, were much regular relative to the background Kastner exponents, for example. Okay. And this could affect, let's say, okay, you would like to have a 1-to-1 correspondence between initial data at equals 1 and initial data at the singularity. And this map, you know, how regular is it, etc. Okay, it's one interesting question in this type of problems. And we have a beautiful work by Warren that he didn't tell us about. Older one. He has a lot of many beautiful works, so he cannot talk about everything. But he proved that in certain linearized setting for this problem, there is actually certain variables lose derivatives. And this cannot be avoided. So in his formulation of the linearized gravity equations, certain variables lose derivatives. Okay, and you have to ask yourself whether this is a phenomenon of the actual Einstein equations, etc. And there's, okay, and more generally, for this type of systems with degenerate borderline, let's say, coefficients, like 1 over t. So if you have degenerate, let's say, hyperbolic systems, okay, depending on how degenerate it is, this loss of regularity cannot be avoided. Okay, so for linear equations, this has been established. And okay, so that's one question. Oh, time flies. Okay. All right, and now let's introduce a little bit of the framework. Okay, so the variables that we know and love now, at least myself and maybe some other people, have to do with a splitting, D+1 splitting of the metric. You have a lapse, zero shift. You define an orthonormal frame that is kind of propagated so that it's adapted to the level sets of T. And then you have connection coefficients. Okay? So the second fundamental form, contracted relative to this frame, the spatial connection coefficients, and a CMC slicing that we heard from Hans. And the Kastner values in this setting take this very simple form. Okay? So in particular case, like 1/T. And the result that we have with Jared says that there is approximate monotonicity. So somehow there's cancellations for the full range of Kastner parameters that I personally didn't think it was possible, but okay, it took a while, and we saw some new structure that helped us to get this. So basically, for the up to n-1 derivatives, you have the optimal estimate for k, and hence for the Kastner exponents, the final Kastner exponents, and you lose a little bit at the top order. And the spatial derivatives are just less singular in some sense, which is enough. Like this is what you want for getting singularity formation. To get the spatial geometry that Hans talked about, you need to lose more. Okay, but at least for the Kastner exponents, for example, when they're distinct, you know that they're going to be as regular as the the space where you have optimal estimates for the renormalized second fundamental form. Okay, you have blow up of curvature, like all the good things that all the previous results had, but now you have it for almost top order. Okay, and this is consistent. So for the refined estimates that Hans talked about, the full spatial geometry, then you have to lose. And you lose, so it depends on the background Kastner exponents. So one question still remains whether this loss is actually fundamental or not. Okay, so that we don't really settle this. Okay, so this is the system. We have a first order PDE for the connection coefficients and the second fundamental form. So this is the ADM type system. There's an OD for the frame, a nice elliptic equation that has a favorable potential term for the lapse, and the wave equation for psi. And as I said, there's two ingredients. One is the OD part that drives the blow up, that also we heard from Warren. And you can easily read it off in this framework. So in order to get the spatial connection coefficients, you need to consider a special combination that has to do with the structure coefficients that also Hans told us about. And from these, you get immediately, if you assume the right-hand side is error, you estimate it, let's say, using the bootstrap assumptions or the top order estimate. Then you get the behavior you like at L infinity. Okay, then the top order part is the second ingredient, which is important. And in order to see these cancellations, turns out you have to use both constraints. So the Hamiltonian constraint, I mean, we didn't use it in our previous work, but I think for the near isotropic case, Rodniansky spec used it. Then an interesting feature is that you don't really have to estimate the estimates for the lapse kind of separate, and this is different relative to the isotropic case where they did it the other way around. Somehow you first close the lapse, and then or at least you get some estimate. Everything has to be done together, but somehow the important part for the borderline terms can be first treated for the lapse and then get the other variables. And the main new ingredient is a nice ODE for the trace of the structure coefficients. So here, the equation for the connection coefficients has derivatives of k, right? But if you trace it and use the momentum constraint, this goes away, and you only have terms which are more regular. So that if you commute with n derivatives, this is at the level of your energy. So this means you can, if in the main energy identity that you have for the rest of the variables, you can add a multiple of this, and you don't lose derivatives. So this is one key feature. Okay, and let me just glance through the cancellations. Of course, you won't have time to really examine if it's true. I hope we didn't make a mistake, because if a plus is a minus, and then it all falls apart. Huh? Okay. But we've checked many times. I trust Jared. Maybe we should also put it on ChatGPT. I don't know. But anyway, so this is the main energy identity. If you don't include, oh, what did I do here? Okay, so this term should not be included. So this is the main energy identity. Okay. All right, as you see, there's some borderline terms here. Okay, and you can check whether they can be absorbed using the favorable ones on the left-hand side, and then there's sort of the ones which are mixed, and okay, you can try to do Cauchy-Schwarz, whatever trick you like, and see whether they can be absorbed, and it's not possible unless you have the near isotropic. You know that all Kastner exponents are near equal. Okay, and now you add this guy, so the top guy. This should also be red. And this gives you an extra line, okay? And you observe some cancellations. But still, for example, here, you see K dot. So dot is for, let's say, top order. So commuted with n derivatives. But K dot doesn't appear on the left, right? So there's no favorable term that contributes to this. So how do you absorb this guy? Okay, and it turns out that this last line can all be removed using the Hamiltonian constraint. Okay, so what you're left is the top identity. So now we've narrowed it down to only this. Okay, and it turns out that this can be exactly. So if you do Cauchy-Schwarz and Young's inequality, and you use the algebraic identities for the squares of the Kastner exponents, you exactly. So in equality, you kind of barely absorb the terms on the right-hand side with the ones on the left. And the only favorable part, borderline term that you're left with is the one that corresponds to the structural coefficients with distinct indices. So this is never used because if you look at the original ones, so all of these, whenever there's a spatial connection coefficients, it has double indices. So somehow the one with this distinct indices doesn't come into the structure of the borderline terms. Okay, and once you have this, you can estimate the error, and the main point is that the borderline term of this guy is of size epsilon, like the coefficient. Okay, and this is all you need to close the top order estimate. So once you have this, you integrate in space, and you basically, once you estimate the error, you get the top order the desired top order estimate. Okay, thanks a lot.